balancing redox reactions. And thing you need to remember is that they are always coupled. What I mean by that is that if you have an oxidation, you have to have a reduction. You can't have one without the other. You can still solve, say, the electrochemical potential for a half reaction. That's just based on the potential for that half reaction. But in reality, it can occur in the real world, because if there's no chemical or partner to accept the electrons, then the electrons are never given. Okay, it's like someone who's generous, who wants to donate and wants to donate a certain amount of monetary award. There's got to be some receiver there. You can't just donate it to thin air. Okay, same with electrons. If they want to give up electrons, there's got to be a species that will accept them. Otherwise, the reaction will work. So we say that the reactions are coupled. Okay, they're coupled. So whenever you talk about a reaction that's coupled, we always talk about a reaction in which oxidation occurs and reduction occurs. Just real quick. Okay, and when the oxidation reaction happens, like what you see here, then the species loses electrons. Okay, oxidation is when the charge goes up. In order for the charge goes up, it's got to shed its negative charge. When it shed its negative charge, then it's oxidized. That means you lose electrons and you oxidize. And that species is called the reducing agent. And the reason why it's called the reducing agent is because it's the one that's donating electrons to reduce its partner. The reduction process is when a species drops down in its overall charge. Okay, it goes from a +1 to a 0, or a -1 to a -3. Okay, anything that reduces its charge is going to be a reduction process. And reduction means that it's going to gain electrons, because remember, electrons are negatively charged. So when you add more negative, then the negative charge goes up, or the charge decreases because of the minus on that. Chemicals that undergo reduction are the oxidizing agent, because by accepting that electron, it causes its partner to give up the electrons and its partner gets oxidized. So make sure you understand the difference between an oxidizing agent and a reducing agent. Okay, now here are common rules that you should remember from Chem 200. That is how to determine the oxidation state of any element in a formula. The priority goes with fluorine, oxygen, okay, nitrogen. The priority is always based on the most electronegative element. So fluorine's always -1, -1, yeah, -1. Oxygen's -2, except when it's bounded to a fluorine, then it can be a -1, or it can be a peroxide or superoxide, in which case it's a -1/2. Those are weird exceptions. Then metal, as found, it's in neutral. The neutral metal has an oxidation state of 0. Diatomic molecules like chlorine and hydrogen, H2, Cl2, Br2, F2, they have oxidation state of 0. So here's the rules in terms of assigning oxidation numbers. And then just based on these rules, you can figure out the oxidation state of any element that is combined with these elements right here. So make sure you review these, because they're important in determining oxidation state. Oxidation state is simply the charge of that particular element or polyatomic ions, okay? Now let's take a look at balancing redox equation. When you balance a redox equation, you want to remember these rules. This is the best way for me to explain how to balance redox equation. There's other methods out there, and the other method requires you to understand how to assign oxidation states. This just requires you to be mechanical in carrying out the process. The first step is to always figure out which is the oxidizing reaction, which is the reducing reaction, which is the oxidizing agent, which is the reducing reagent, because you need to break up the overall reaction into halves. Each half will either be an oxidation or a reduction, but you need to do that. So that's the first thing that you need to do. You need to identify the oxidized and reduced species and then write that half reaction. Sometimes that's the most difficult part in the process. And I'll show you examples of what I mean. Now that you have each half reaction, you need to balance each separately, okay? So it's basically two problems in one. You need to balance each separately. The first step you need to do is balance any non-hydrogen and oxygen element. What do I mean by non-hydrogen and oxygen? Elements like carbon, elements like chromium or silver or sodium. If it's not a hydrogen or an oxygen, you balance those first and make sure they're the same in both sides. And then once that's balanced, don't even worry about the charge at this point. Then you balance the oxygen right here by water. Why water? Because you can't add just oxygen into the chemical or O plus into the chemical. That species is not readily available in your medium that in which the reaction occurs, but water is, because water is the solvent of choice in generally a lot of these particular reactions. We're dealing with aqueous medium. So make sure that you balance the oxygen with water. Some of the water get oxidized or maybe reduced depending on the chemistry, okay? But now when you balance things by water, you also introduce hydrogen. That's okay. We balance hydrogen by H plus. And you might say to yourself, well, okay, H plus is good if it's acidic. Why if it's basic? Well, we'll make that correction shortly. Okay, we'll make that correction shortly. How about if you have, if it's basic, then we'll make that correction. So hydrogens by H plus. Now that at this point, what you need to do is stop and pause and just double check your elements, okay? Because if you go further down, you might get lost in the calculation, or you might lose time when you try and correct it. But if you check the elements at this point, remember you're balancing half reactions separately. So this would be like the first half reaction. Then you can balance the charge. The charge will always be need to be balanced at this point, and you balance charge by electrons. Electrons are negative. So when you put electrons either to the reactant or the product, the charge can only, the overall charge in each side can only go down because electrons are negative. You can never raise the charge. You can always lower the charge because it's by electrons. Once that happens, then you go to the other half reaction. Okay, don't worry about the number of electrons you have. As long as it's balanced, you're good. Go to the other half reaction, balance the non-hydrogen and oxygen elements first, balance the oxygen by water, balance the hydrogen by H plus, and then balance the charge. Now take a look at their two-half reaction. At this point, your two-half reaction should have electrons in opposite sides. One of the reaction will have electrons on the left, which means that it's gaining electrons. If it's gaining electrons because the electrons are reactant, then that's the reduction reaction. The other half reaction should have electrons on the right, which means it's losing electrons. If it's losing electrons, it's an oxidation, okay? Nevertheless, they should be in opposite side. If they're in the same side, you made a mistake. Go back and check your work. You made a mistake somewhere, okay? They have to be in opposite side. Now that they are in opposite side, you need to look at the number of electrons that you have. If they're the same, good. You just add the two-half reaction. If they are different, then you look for a common number. Let's say you have 3 electrons on one reaction and 5 electrons on the other. Well, common number is 15. You need to multiply the half reaction with 3 by 5, which will give you 15 electrons. You need to multiply the half reaction with 5 electrons by 3 to give you 15. That way the electrons cancel. The electrons always have to cancel when you add the two-half reaction. Otherwise, it's a no-go. The reaction won't work. The electrons have to cancel because when you have your net reaction, no electrons can be shown. You can have water, you can have H plus, but no electrons. They have to cancel. Okay, so that's what this is. Now that you've canceled the electrons, then your work is done. Okay, so let's take a look at this reaction right here. Okay, I'm going to walk through this. So this is iodine, I minus, going to I2. You can see that I2, the oxidation state of I2 is 0. Why? Because that's the way it's found in nature. I minus, the oxidation state of I minus is -1. So -1 going to 0, that's the oxidation reaction. The charge is going up. Oxidation reaction means that the electrons is probably going to be found on the right side because the electrons are going to be lost. The other chemical is S2O8. That's thiosulfate going to persulfate, S2O4. And even though it looks like the charge are the same, this sulfur right here is, see, oxygen's -2, -2 times 8 is -16. -16 and minus, yeah, that's -16. -16 and -2, that's -18. -18, the sulfur here has got to be a positive 9. A positive 9 will make this a positive 18, a -16, that, sorry, the sulfur here should be a positive 7. So the oxidation state of sulfur here is positive 7. The oxidation state of oxygen here is -2. -2 times 8 is -16. -16 and a positive 14 makes that -2. That's how you play this game of oxidation state. So this is positive 7. Let's go over here to this side. Okay. Oops. This side right here, this whole thing is -8. 2 times oxygen always has a -2 oxidation state because that's the most electronegative element. So that whole thing is -8. 4 times 2 is -8. And then there's a -2 here. That means that this sulfur is probably a positive, let's see, 8, positive 7, positive 6. 6 divided by 2 is positive 3. So if you have a positive 3 here, that will make that positive 6, and a -8 here, that gives this whole thing a -2. So what we're doing is we're going from positive 7 to positive 3, and so that's a reduction process. See how we determine the oxidation state for that? It's not required in this problem, of course, but that's how you would walk yourself through in determining the oxidation state. The charge times 2 of sulfur plus the charge times 8 of oxygen has to equal -2. Okay, the charge times 2 of sulfur, 3 times 2 is 6, plus -2 times 4 is -8. Positive 6 and -8 gives you a -2 overall. The sum of the charges of the element have to equal the whole charge. Anyway, let's look at, so this is under acidic medium, and what we're going to do is look at the 2-half reaction. That's the oxidation, that's a reduction. We're going to balance one of them first, doesn't matter which one. And here we balance the non-hydrogen and oxygen element first. So we put a 2 in front of the iodine so that there's 2 iodine. And then on the left side, we see a -2. On the right side, we see a 0. So we need to put 2 electrons on the right side. Now the charge is balanced. Now we can do the second reaction. We have S2O8 here, S2O4. If you look, the sulfurs are balanced, so we don't have to worry about the sulfur. Oxygen is 8 here, but 4 here, so we need 4 waters on the right side. That way we have 8 on both sides. So 4 plus 4 is 8. By introducing 4 waters, we introduce 4 hydrogen. We introduce hydrogen by 8H+. Okay, now all the elements at this point should be balanced. We've got 8 hydrogens, 8 oxygens, and 2 sulfurs. Let's look at the charge. This side is -2. This side right here is +8, -2. This side's +6. Okay, this side's +6. We need to make it either +6 on both sides or -2 in both sides. You can only get to -2 with electrons. So don't try and get um, -6, a +6 on both sides, because electrons only brings the charge down. So in order for both sides to be -2, you put 8 electrons here, the 8 negative and the 8 positive cancels, and you get -2. Look at the number of electrons. There's 8 here, there's 2 here. The common number is 4. Okay, common number is 4. Make this half. No, that would not work, because then you would get a fraction here. The common number is 8. So 8 is good for the second reaction. You need to multiply the top reaction by 4. When you do that, it becomes this. Now you can add it to the second reaction. The electrons will cancel. Again, this process is the most easiest, but it can be tedious. Okay, it can be tedious. Then when you cancel the electrons, this is your net balance equation. Notice that the original equation, I S2O8, I2 S2O4, is slightly different from the bottom, but S2O8 are the same, I2 are the same, S2O4. The only difference is that you're introducing water and hydrogen. And that's okay, because in aqueous medium, those chemicals exist. When you have a redox reaction, you got to be prepared to introduce water and H plus. Okay, that's the only way you're going to get hydrogen in your reaction. If it does not show hydrogen initially, or if there's a deficiency in oxygen, it comes through water or H plus. Now, let's take a look at this reaction under basic conditions. The only difference is that you need to add one more step. And that step is to eliminate the hydrogen plus by adding H plus plus OH minus, forming water. And how you introduce that last step depends on where the hydrogen is in your balance equation. So let me show you an example. Here's another example. We've got hydrogen peroxide plus chromate, dichromate, goes to chromium plus oxygen. We look at the reaction. To balance this reaction, the chromium. So the chromium reaction is what we are balancing first. Cr2O7, we start with this guy right here, Cr2O7. Yeah, go back. Get a pen so that you guys can see this. Okay, so right now we have Cr2O7, and it's going to chromium. That's what we have right here. We need to put a 2 right here in order to get 2 chromiums on each side. Now we look at the oxygens. Chromiums are balanced. The oxygen is 7. There is no oxygens on this side. Don't worry about this oxygen. That's not in your half reaction. Okay, don't worry about this. That's not in your half reaction. You need to introduce oxygen by water. To get 7 oxygens here, you need 7 waters, which means you need 14 hydrogens on the left side. Okay. Again, the steps are non-hydrogen and oxygen elements first, oxygen by water, hydrogen by H plus. Once we have our H plus here, we double check and make sure all our elements are balanced. Then we look at the charge. We got a positive 14 here, we got a -2 here. So this side is positive 12. This side is positive 6. So we can only bring the charge down. So this positive 12 needs to be brought down to positive 6. We introduce 6 electrons. This side now becomes a positive 6, and this side is positive 6 by virtue of 2 chromium plus 3. Now we go to our second half reaction. Our second half reaction is this right here. Let me clear that real quick. Okay. Let's see. Pen, erase. Okay, no, that didn't work. Should be an eraser in my tools here. Okay, I can't figure it out, and I don't have time to figure this out. But let's take a look at hydrogen peroxide going to oxygen. Hydrogen peroxide going to oxygen, there's, again, we don't have to worry about non-hydrogen and oxygen element because there are already uh, just hydrogen and oxygen elements here. So oxygen, two, two oxygen, that's fine. We don't have to introduce water. Two hydrogens, hydrogens by H plus, two H plus. The oxygen and hydrogen are balanced. Now we need to balance the electrons. There's a positive two here, there's a zero here. So we need to put in two electrons on this side. We see that electrons are in opposite side. On the first reaction, it's on the left. On the right, on the bottom reactions to the right, that's good. The common number of electrons is 6. We need to balance the multiply the bottom by 3. That way you get 6 electrons. Then we just add them up. The electrons should cancel. In the end, we get 14 here, but we have 2 times 3, 6 hydrogens here. So that leaves us 8 hydrogens net. We still got 3 hydrogen peroxide. Remember, we're multiplying the whole bottom reaction by 3. We still have 1 dichromate, 2 chromiums from here, 3 oxygens because we're multiplying the bottom reaction by 3, and then there's 7 waters. There's 7 waters from this reaction. That's your balance equation under acidic medium. You see how hydrogen is right here? Well, remember that in order to get rid of hydrogen, we need to add this reaction right here. H plus OH goes to water. So how do we add this reaction so that the H plus cancels? Well, the only way this is going to work is when we put the H plus on the product side and the water on the reactant side. So what we're going to do is put H plus down here. Okay, and then we're going to put 8 H plus. Why 8? Because we need to cancel out 8 H plus. That means that we need 8 OH here. So we're just writing the reverse of the reaction I just wrote previously. And then that will be in equilibrium with 8 waters. This step is pretty easy. It's just a little bit tedious. Okay. Then we add 2 reactions. We add the 2 reactions. And that's what you will see right there. The H plus and the 8 OH is on the right, 8 waters on the left. And then when you add that all up, what you end up with is this. And see how the hydrogen now becomes hydroxide? Now you're under basic medium. That's the only step you need to remember if the problem tells you specifically it's under basic medium. Otherwise assume it's under acidic medium. So that's how you balance these equations, okay? It's not so difficult. Here are other examples, and here are your activity. So let's take a look at your activity because I want to go through a couple of these things. Let's take a look at this right here, okay? Oops, let's go back. Let's take a look at this right here because you might be asking, let me get my pen out. This reaction right here, you need an oxidation and a reduction, okay? Now the question is, well, I only got 1 reactant. How can I get 2 half reactions from that? Well, remember, you don't just have 1 molecule of iodine in your reaction mixture. You have moles and moles. Some of them will undergo oxidation, maybe. Some of them might undergo reduction. Okay, so those are your half reaction. I2 going to IO3 minus, that's one out of your half reaction. I2 going to I minus. So if you don't have enough of the chemicals, remember that those chemicals are not restricted to just doing an oxidation or just doing a reduction. Some of it might undergo oxidation, some of it might undergo reduction. So that's your 2-half reaction for this case. Okay, let's take a look at this right here. Again, this is a classic example that this will go to chromium. Chromium will form this, but this, however, is tricky. And the reason why this is tricky is because you can't have the chromium going to oxygen, because you can't have CrO4 going to oxygen, because that species doesn't have chromium. And in order for you to introduce chromium, you need to bring this chemical in. According to this reaction, I have CrO4 going to CrOH3. But another chemical that is not obvious to you is water. Okay, so your second reaction is just water, even though it's not written there. It's always available. Water going to oxygen 2-. That's how you get water. In water, the oxidation state of the oxygen is -2. Here, the oxidation state of oxygen is -1. Each oxygen in O2 2- has to be -1 in order for that to be correct. So that's a peroxide. Whenever oxygen is not -2 but -1, it's called a peroxide. So that's your other half reaction. You got to be sort of smart about these things, okay? Let's take a look at this right here, because this one's a little bit tricky, okay? One of the half reaction is going to be KMnO4, and the only potassium that I can see is here. Okay, the problem with KMnO4 going to potassium chloride, and let me write this in my iPad so that you guys can see this. Okay, let me show you what I just did. This is probably the hardest type of problem. And again, it's about starting rather than the process. And I'll do this problem completely for you guys so that you guys can see. Whenever you pick a half reaction, you got to make sure that the elements that are not hydrogen or oxygen are in both sides. So first half reaction would be KMnO4. Potassium is found here, so I got to introduce that. But I introduced chlorine, so I need to introduce chlorine here as HCl. And then I need to worry about manganese, so that's MnCl2. Now I have potassium on both sides, manganese on both sides, and chlorine in both sides. That will work. The other half reaction is going to be based on the chemicals I didn't use. I didn't use chlorine. And chlorine can only come from, or it's most likely coming from HCl. So that's my second half reaction. I'm going to save that for my second step. So for the first step, let me clear this for you. Let me clean this up. Okay, let me show you how to balance this. So 1 potassium, 1 potassium, that's good. 1 manganese, that's good. 2 plus 1 chlorine, I need 3 hydrochloric acid right there. Now all the potassium are balanced, all the manganese are balanced, and I got 3 chlorines on both sides. Okay, now the next step is to balance the oxygen. I got 4 right here, so I need 4 waters. Okay, 4 waters brings in 8 hydrogens on this side. Okay, 8 hydrogens on this side, but I already have 3 here, so I need 5 H plus on this side. Now, all the elements should be balanced. I've got 1 potassium, 1 potassium, 1 manganese, 3 chlorines, 2 plus 1 chlorine. I got 4 oxygens, and I've got 3 plus 5 hydrogens, 8 hydrogens. The very next step is balance the charge. This side is 0. The potassium chloride 0, the manganese chloride 0, the water 0. This side, positive 5. I need 5 electrons in this side. That would be the balance half reaction. Now I look at my second reaction, HCl going to Cl2. And I can see I need 2 potassium chloride here. Okay, and you can see that I don't need to worry about oxygen. I do need to worry about hydrogens. Two hydrogens there. This side has 0. This side is positive 2. I need 2 electrons here. So I told you that the hardest part is actually getting started. Once you have the two-half reaction, it's pretty easy monomically. I can see right now that my common number is 10. So I need to multiply this top reaction by 2 and this top reaction by 5 and then add the 2. And then when I add it, the 10 electrons on the right should cancel out with the 10 electrons on the left. And that would be my half reaction. So that's a good example of how to balance complicated problems like this. And remember that you're always looking to make sure that the non-hydrogen and oxygen elements are going to be on each of the sides in your half reaction. Okay, so this is a really good example to cover. This
When
is
you're trying to balance that, I kind of understand the balancing the O's and the H's,
right.
but I got confused when you balance it when you put a 5 electron
Okay,
negative.
let me do
Like, why
this.
would that be placed there?
Let me show you what's going on. Okay, let me erase this real quick. KMNO4 is one of my reaction, and then I said that I'm adding HCl to that, and then it's forming KCl plus MnCl2. And in order for this equation to balance, I remember that we had my potassium is balanced, my manganese is balanced. I need 4 waters here to balance my 4 oxygens. And then I need, there's 3 here. Okay. And I need 5 H plus. That gives me 8 on the left side, 8 on the right side. And then my second half reaction was HCl going to Cl2. 2 here, 2 H plus here, and 2 electrons here. Now you see how I forgot to put electrons on the top side. I have positive 5 here, but 0 here. So this side has 0. This side has positive 5 right here. So I need 5 electrons here. Positive 5 and negative 5 equals 0, and it balances the left side. So what we have at this point is the following. We have this half reaction at the top and this half reaction at the bottom. There's 5 electrons here. There's still only 2 electrons down here. That when you add the 2 electron half reaction as is, you don't get a net 0. So what you need to do is you need to take this reaction and multiply it by 5. Why by 5? Because then this gives you 10, 5, 10, and 10 electrons. The 10 electrons will not cancel the 5. That's why you need to multiply this equation up here by 2. Because by multiplying it by 2, now I get 10. Let me change colors here. 10 electrons here. I got 2 here. I got 6 here. And I got 10 here. I've got 2 here. I got 2 here. And I got 8 here. Now the electrons can cancel. The ultimate last step is the electrons need to cancel. Otherwise, your equation will never be balanced. In the end, you need to make sure that the electrons cancel. And so this will show up as 2KMNO4 plus 6HCl plus 10H plus 10HCl going to, so I've taken care of this, I've taken care of this, I've taken care of this, and I've taken care of this right here. That's on the left side. On the right side, I have 2 KCl plus 2 MnCl2 plus 5 Cl2 plus 10 H plus. Okay, the 10H plus here will cancel with the 10H plus there. Okay, and it looks like that we're pretty good in terms of all of this. I need to reduce this further. 2, again, it's just a matter of doing arithmetic. 2KMnO4 plus 16HCl goes to 2KCl plus 2MnCl2. Yeah, 2MnCl2 plus 5Cl2. At this point, you should be able to look at all the elements and balance. I've got 2 potassium on this side. I've got 2 potassiums on this side. I've got 2 manganese on this side. I've got 2 manganese on this side. Okay. I've got 16 chlorines on this side. I've got 10 here, 4 here, and 2 here. I've got 8 oxygens on this side. I don't have 8 oxygens on the right side. Where am I missing oxygens? Oxygens, I got 10 here. Where did I miss my oxygens? Anyone figure that out? Oh, I forgot to add my
Okay, Google.
Were you supposed to
8
add
waters.
water?
I forgot my 8 waters, right? 8H2O right here. Thank you. So 8 oxygens here, 8 oxygens here. And then finally my hydrogens, I've got 16 hydrogens here. I've got 16 hydrogens there. Yeah, I forgot my water to bring down. It's easily confused. And both sides are 0. But that's basically why I introduced the 5 on the top and the 2 on the bottom. I have to cancel my electrons. They cannot show up in the net equation.
So going back to that blue portion of the text, the hydrogens plus added are considered protons, which means it has essentially 5 less electrons. That's why you're putting
Exactly.
that 5e on that left side. Okay.
Right. Think of the hydrogens plus as just positive 5 in that side, right?
And
yeah, they're
since
protons.
H is the only charged particle in that side, and whereas the other side doesn't have anything, that's why you put those 5 electrons.
Exactly. Good point. And it just takes practice. You got to practice these things because you always see different combinations. But if you double check along the way and don't make dumb mistakes like me and forget to carry one of the chemicals down, everything should balance. This is your activity right here. Okay, I'm just going to walk you through this. The ones that I circle in red because those are the ones that are probably difficult to start. Potassium, KBrO2. That particular chemical will probably go to KBr, and that's it. KBrO2 will go to KBr. Why? Because I don't have to worry about oxygen because I can introduce oxygen by water. So there's a potassium on both sides, a bromine in both sides. The other half reaction would be KCl. KCl will go to Cl2 and KBr. But by introducing KBr, I need to bring in HBr as well. So your second half reaction is KCl plus HBr goes to KBr plus Cl2. Okay, that way you get all the elements on the left to be equal to the right. Don't worry about oxygen and hydrogen because they come in via water. Let's take a look at this reaction. NO2 and water goes to HNO3 and NO. So this is an example like what we did with iodine. NO2 will go to HNO3 and NO2 will go to NO. The water in here is just running interference. The water will show up naturally once you balance the equation. If you balance this equation correctly, the water will show up on the left. So don't worry about water unless you have to bring it in because you have to balance a peroxide. Okay. Um, this reaction right here, I2 going to NH4I, but by bringing in NH4I, you also bring in nitrogen. So the first half reaction is I2 plus NH3 going to NH4I. The second reaction is just NH3 going to N2. Okay. This reaction down here, this seventh reaction, KBr going to potassium nitrate and Br2. Okay, but by bringing in potassium nitrate, you also bring in nitrogen. So KBr and HNO3 goes to KNO3 and Br2. Once you bring in an element on the right side that is not a nitrogen and hydrogen, you have to introduce it on the left side. That's why I brought in HNO3, because you can't bring in nitrogen from air, or it's not present in water. The second half reaction is just HNO3 going to NO. That's the only other chemical that I didn't use in the first part. It takes practice doing these things, and that's why you have a whole bunch of problems like this. This is an interesting problem right here. Br2 goes to BrO3, and Br2 goes to Br. Okay. This one right here, PbO2 goes to PbSO4, and Pb goes to PbSO4 and SO4. Sorry, the first reaction is PbO2 plus SO4 goes to PbSO4. The second is Pb plus SO4 going to PbSO4. You just have to practice these things, and if you practice them, then it'll be secondary. Okay, but that's basically what your activity is all about.